Okay, at the end of the last lecture, I said we would be walking through an example. So let's do exactly that. Here we have two half reactions. You'll notice that they're both reduction half reactions. They both have, electrons on the product sides. In both cases, the reactants are gaining electrons. So we're talking about reduction. The first reaction, the one up top, is iodine plus 2 electrons goes to form 2 iodide. The one on the bottom is hydrogen peroxide plus 2 hydrogen 1 plus 2 electrons goes to form 2 water molecules. And over on the right we see their reduction potentials. E standard equals 0.54 volts for the iodine reduction, and E standard equals 1.78 volts for the peroxide reduction. So the question is, which one of these is going to be reduced? Which one of these is going to be oxidized? Remember, the way a battery is set up, you have both the reactants and the products set up. And then it's just the nature of the chemicals that drives the reaction in one direction or the other. So, which is it going to be? Is iodine going to be reduced and hydrogen peroxide oxidized, or vice versa? Well, to figure that out, you need to look at the potentials. In order for it to be a proper galvanic cell, the potential energy of the cell needs to be greater than zero. The voltage potential of the cell needs to be greater than zero. Okay? And we hop back to the previous slide, and what we see is that E standard of the cell is equal to E of the cathode minus the potential of the anode. So, now coming back to our reactants, which is it going to be? Which one's going to be the cathode? Which one is going to be the anode? Is it 1 minus 2 or 2 minus 1? The answer is going to be whichever one gets us a positive number. So it's going to be the second one minus the first one. Number 2 minus number 1. Because that's 1.78 volts minus 0.54 volts gets you the potential for the cell, 1.24 volts, positive. Okay? That's all there is to it. And what that means is that the second reaction, or the second half reaction I should say, is going to stay exactly as it is, a reduction reaction. It's going to be our cathode. The other one is going to be our anode. That's going to be where the oxidation takes place. So our first half reaction is going to have to get flipped around. And once you've done that, you go ahead and you add your two half reactions together. And it's going to look a little something like this. So you just bring it down, you flip it around. And what you get is, 2 iodide goes to form iodine plus 2 electrons. And notice when you flip it around, just like with enthalpy, you change the sign. Okay? So subtracting a positive is the same as adding a negative. Okay? And just like with balancing redox reactions, anything that appears on both sides of the arrows is going to cancel out. In this case, all it is the 2 electrons. And this example happens to be nice and simple in that the electrons are the same, so that saves us a little bit of multiplication. But even so, if there had been hydrogen or water on both sides, anything like that, then those would have been canceled out as well. So once you're done canceling, easy enough in this case, you add them together. You get hydrogen peroxide plus 2H plus 2I minus yields 2 water plus iodine with a standard cell potential of 1.24 volts. A little bit easier than balancing your redox reactions before. And that's because most of the work has already been done for you with the H plus and the electrons and the water and so on. But I want to draw your attention to the two electrons. Those are going to be very important in not too long from now, in a short time from now. Those are going to be kind of a big deal. They don't play an important role just at the moment, but they will. But for now, I want to go ahead and throw another example at you that's going to have different numbers of electrons. So here is our next example. Our first reaction is nitrate, NO3 plus 4 hydronium plus 3 electrons yields nitric oxide. Remember, that's one of those weird ones. It's just an exception. Nitric oxide and 2 water with a standard reduction potential of 0.96 volts. Our second reaction is lead-4 oxide, that's PbO2, plus 4 hydronium plus 2 electrons yields lead-2 and 2 water with a standard reduction potential of 1.46 volts. So, which one of these is going to be our anode with oxidation? Which one is going to be our cathode, which is going to be reduced? Well, remember that the standard potential of the cell is the cathode minus the anode, and it always has to be greater than 0. So you just look for the bigger one. The bigger reduction potential is always going to be your cathode. And in that case, that's half reaction number 2. So we're looking at 2 minus 1. So since reaction 1 is oxidation half reaction, we're going to have to flip it around. And when we do that, it becomes nitric oxide plus water yields nitrate plus 4 hydronium plus 3 electrons with a potential of negative 0.96 volts. Remember, you got to flip the sign when you flip the reaction around. So, if you'll forgive me for tidying things up just a little bit, you can just move things up to the top a bit. All right. Now, note that now we have 2 electrons for our reduction. We have 3 electrons for our oxidation. Just like with balancing a redox reaction, you need to make the electrons disappear, so we are going to have to multiply our 2 reactions, or 2 half reactions, excuse me, just like with balancing a redox, okay? Because that's really what we're doing, is we're doing the last few steps of balancing a redox reaction here. And when you do that, that means that you're multiplying this top reaction by 3, you're multiplying the bottom reaction by 2. And that gives us these 2 new half reactions. 3 PbO2 plus 12H plus 6E minus yields 3 Pb2 plus 6 water with a potential of 1.46 volts. And 2NO plus 4H2O yields 2NO3 1 minus plus 8H plus 6E minus with a potential of negative 0.96 volts. Now, something I absolutely have to draw your attention to, something that is vital, look over at those voltages on the right-hand side. Okay, 1.46 volts, negative 0.96 volts, they have not changed. Okay, when you multiply those reactions, the potentials do not change. Okay, those numbers stay exactly as they are. I'm stressing that because it's vital that you remember that. If you don't remember that, you'll start getting wrong answers, and then you'll cry. You'll cry, and you'll cry, and you'll cry. Okay? So let's go ahead and add these 2 reactions together. And when you do that, you're going to start canceling things out. Anything that appears on both sides of the arrow are going to get canceled out. So first things to go are going to be those electrons. Okay? Those cancel out perfectly, which is exactly what we want. It's what we need. It's why we multiplied things. So the electrons are gone. Next up is our H+. We have 12H plus on the reactant side up top. We have 8H plus on the product side down at the bottom. Those are going to cancel out, leaving us with 4H plus on the reactant side. And finally, our water. We have 4H2O on the reactant side and the bottom reaction, and we have 6 water on the product side on the top reaction. So those are going to cancel out and leave us with 2 water. So when we add our reactions together, we are going to end up with 3 PbO2 plus 2 nitric oxide plus 4H plus yields 3 Pb2 plus 2 nitrate plus 2 water with a standard cell potential of 0.50 volts positive. And once again, I want to go ahead and point out our electrons. Okay? those 6 electrons that get lost by nitric oxide and they get picked up by the lead, those are something you're going to have to remember. Okay? You're going to have to, when you balance these reactions, just sort of keep a hold of that number. Note it down somewhere, okay, for future use. Okay? Even though these 6 electrons are invisible in the final reaction, they are important for later problems, for other information that we can suss out from or related to galvanic cells. Speaking of which, let's go ahead and start looking at the places where those electrons might come in handy. That degree symbol, it's not actually a degree symbol, it's something else entirely, but whatever. It means standard conditions. So what about other conditions? Okay, you don't always have 1 molar of stuff. You don't always have 1 atmosphere of stuff. But you need to be able to calculate voltages and free energies and things like that for non-standard conditions. Okay? So we are going to end up with a large number of mathematical equations. The derivations, if you're interested in that sort of thing, are in the textbook, but I will not be providing them here. But let's go ahead and take a look at the first set of equations. First up is the relationship between Gibbs free energy and our cell potential. Delta G is equal to negative NFE, or delta G standard equals negative NFE standard. Okay. N is the number of electrons. Okay. That is the number I've been pointing out, the number that becomes invisible. Okay. In this previous reaction, it was 6 electrons. In the reaction before that, it was 2 electrons. Okay. This is where that shows up. Electrical potential, this voltage is really useful, but so is Gibbs. You really need both of them. F is Faraday's constant. It's just the amount of charge carried by a mole of electrons. A mole is a really large number of electrons, but each electron has a very small unit of charge. Nevertheless, all told, there are 96,480 coulombs of electrical charge in a mole of electrons. The negative sign, that's because we're talking about a spontaneous reaction. A galvanic cell is always going to be spontaneous, and a spontaneous galvanic cell, that means a positive voltage. But spontaneous means negative Gibbs free energy. So it's negative NFE. So let's go ahead and calculate the Gibbs free energy change for the 2 reactions we just looked at. All right, we will work our way backwards for these examples. So we'll start with the previous of our 2 reactions. Lead oxide plus nitric oxide plus hydronium yields lead 2 plus nitrate plus water with a cell potential of 0.50 volts. So delta G standard equals negative NFE standard. So we just plug in the numbers. Okay. Remember I told you to note down very, very carefully the number of electrons. Well, in this case it's 6, so that's N. So it's negative 6 moles of electrons times 96,480 coulombs per mole of electrons times 0.50 joules per coulomb. Joules per coulomb? Yes, that's what a volt is. A volt is 1 joule per coulomb. Okay. So those are just the same thing written differently. And when you multiply all that out, you get negative 290 kilojoules. Doesn't necessarily mean much to you, except that, you know, a negative sign means it's a spontaneous reaction, so it's what we would expect there. But it's something that you can use to get other information, as we'll see soon enough. The reaction before that, moving on, was hydrogen peroxide plus 2H plus 2I minus yields water plus iodine, with a potential of 1.24 volts. And delta G standard equals negative NFE standard equals negative 2 yeah, it's a little harder to see on this one, but and you might not remember that far back, but there were 2 electrons being transferred in this reaction. So 2 electrons times 96,480 times 1.24 joules per coulomb equals negative 239 kilojoules. So again, it's spontaneous, but that number doesn't necessarily mean anything in and of itself. But it's important to have Gibbs free energy because you can use that to get, say, enthalpy and entropy and the temperature at which this is spontaneous versus non-spontaneous, all that sort of stuff, And equilibrium constant, things like that. But those we will explore in upcoming lectures because we have gone a little bit over 15 minutes on this one.